tracing parallel between Coxeter groups and matroids. And I'm going to tell you a conjecture that I find very attractive. It is a problem that requires an acquired taste. So you may find it amazing or something else, but I hope you will at least find it very curious, the phenomenon, numerical phenomenon we are observing. Okay, so there's a very big streamline of research, mostly in representation theory, that goes under the heading of Kazhdan-Lusztig theory. And the classical story starts from that side, where Kazhdan-Lusztig theory constructs, among many other things, the Kazhdan-Lusztig polynomials from Coxeter groups. So maybe I'll start by explaining what Coxeter groups are. So these are particular kind of groups. And roughly speaking, Coxeter group W is a group generated by the so-called simple reflections. And there is an abstract definition for it, and it roughly goes as saying that W is a Coxeter group if it admits a finite set of generators that you call simple reflections that satisfy such and such relations that you would expect from the reflections on the Euclidean or other spaces. So rather than going into the formal definition of Coxeter groups, let me show you or remind you some examples. And maybe the most familiar example would be the group of reflections generated by two simple reflections in the plane, meeting each other with the angle of pi over 3. So here's my one reflection. Let's call it S1. And let's consider another reflection as group of transformations of the plane. And if you consider the set S of these two simple reflections, S1 and S2, and it's not hard to justify that, it generates a Coxeter group, which is S3, the group of permutations of 3 elements. So in the familiar notation for permutation groups, here my S1 would be the transposition of the first and second element, and S2 would be the transposition of second and the third element. And of course, this is a very special case of a Coxeter group. And you can easily imagine already in the case of reflections of plane along a line, you can generate many, many interesting groups following this scheme. So for example, if you play the same game with 3 lines, so that your set S of simple reflections now consists of 3 elements, S1, S2, S3 maybe, then this time it generates an infinite group that is discrete in a certain sense. And if you just wiggle your lines a little bit, then it also generates some other infinite group, which has another interesting property. And the main insight of Coxeter, who initiated this subject from an abstract group theory point of view, was that all such groups share many properties. and you can build a beautiful theory around it. But for us, the most important feature of this setup is that S, this distinguished choice of generators, S, makes W a graded poset. And I'm going to tell you what this poset structure is. So W, when specified in this way, in terms of the distinguished set of generators, it's not just a group, but a poset. So for example, permutation group, every permutation group from this point of view is a poset of n factorial elements. So let me just show you this poset for our example of S3. So it has 6 elements, and on the very bottom of the poset, you have the identity permutation. And right above that, there are 2 simple reflections, our S1 and S2. And above those 2 elements, there are 2 other elements, and the poset structure looks like this. And one is S1, S2, and the other is S2, S1. And the remaining element, so-called longest element, is S1, S2, S1, which in fact is equal to S2, S1, S2. So that's the picture of S3 as a poset. So in general, any Coxeter group W, you can view it as a poset under the so-called Proudfoot order. And it is given by reduced expressions of elements of W. So what is a reduced expression? So remember that W is given in terms of its set of generators S. So for each group element, there must be a word with alphabets in S that has the least length, expressing the given element as a product. Those are called the reduced expressions. Of course, a given element may have many different reduced expressions, but by definition, they all have the common length, which happens to be the height in this poset. So length 1, length 2, length 3. And the Proudfoot order can be specified in many different ways, and one way of specifying is that one element V is larger than another element U if there is a reduced expression for V that contains a reduced expression for U as a subword, not necessarily consecutive. So one of the small miracles, among many other miracles in the theory of Coxeter group, is that in the sentence that I just said, you can replace the part where I said some reduced expression for V contains blah, 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 by another expression saying that any reduced expression for V contains some reduced expression of U. So this Coxeter group side story, I'm just telling you to give some context and give the feeling for the analogy. So you don't need to try too hard to follow all the technical details. So, but already, once you have made W into a graded poset, you can define the Kazhdan-Lusztig polynomial. And again, these polynomials can be defined in many different ways. This is the most combinatorial version. So I'm going to define a one-variable polynomial in variable q for every pair of group elements, u and v in the given Coxeter group W. So let's pretend that W is the permutation group, maybe. And it will define by the sequence of properties that it satisfies. First, P of a Q is equal to the constant polynomial 1 if U is equal to V. And 2, the degree of P, U, V, Q is strictly smaller than 1/2 of the length of V minus length of U. If U is strictly smaller than V. And 3, and this is the important property, at Q times length of V minus length of U, so this LV is my notation for the length of a group element, which is the least length for any given reduced expression of the group element. Times P of a UV evaluated at the reciprocal of Q is equal to the sum over all group elements W in the interval in between U and V. And by this closed interval, I'm referring to the process structure of W. And the sum n corresponding to W is R of a UWQ and P of a WVQ. So of course, this was not the original definition of the Kazhdan-Lusztig polynomial. And in fact, the motivation for Kazhdan-Lusztig was that there is a certain family of polynomials that encodes essential information on the representation theory of simple Lie algebras. And the key insight of them was that these polynomials can be in fact defined in this way, depending only on the group. Not referring to any Lie algebra or anything. It's a combinatorial gadget. So at this point, you should have minor questions. And the first one would be, what is R? But let me just point out that besides that question, there should be another question. So I'm trying to define this polynomial PUV in a certain inductive fashion. So there should be no question about this. And this is a strange requirement, but it is a simple condition. Degree should be not too large. And I have this recursion. But this is not, at least this is not an obvious definition. Because on the left-hand side, you see the object that you want to define, PUV. And there are similar objects appearing on the right-hand side, but one of them is PUV itself when W is equal to U. But if you recall the condition on the degree, you see that this part, in a sense, has coefficient only in the upper half. And temporarily assuming that R U V is equal to constant 1, on this side you have PUV appearing on the other half. So there's no cancellation between this guy and that that sum. So this guy together with that problematic term, in a sense, they form a certain symmetric sequence of coefficients, ignoring sign for the moment. So in order for this kind of definition to make sense, you're requiring a certain non-trivial property for these auxiliary polynomials R. RUU is 1. Yeah, constant 1. So the definition continues, where RUVQ are defined by or RUVQ is equal to 1 if U equals B, and 5 RUVQ is 0 if U and V are not comparable, and 6, and this is the main condition, if length of Vs is strictly less than the length of V, and length of Us is strictly less than length of U for some S in S, so little s is a simple reflection, then R of a UV, R of a USVS, let's do it the other way. R of a UVQ is equal to R of a USVS.
There's a question from the live chat, what this interval precisely is to mean, because so it's just all elements in between.
Yes. So
they're not really an interval in the classical sense, I guess.
In the sense of poset theory. So every element W that is at least as large as U. So that's the condition 6, formulated in terms of the length. And 7, if length of Vs is smaller than length of V, and length of Us is larger than length of U, for S in S, then, may I write here? Okay. R of a UVQ is equal to R of a Q times R of a US VS Q plus Q minus 1 of a R of a U comma VS Q. And fortunately, that's the end of the definition. And amazingly, this definition makes sense. S is the set of generators, the set of simple reflections. So in the case of W equals Sn, you should always keep in mind that S is given by 1, 2, 2, 3, 3, 4, and so on. Transpositions, adjacent transpositions. Yeah. So all this thing is already non-trivial for the case of Sn. So
should we understand
Now, let's accept that the definition makes sense.
Okay.
But at least one can convince at this point that one can devise an algorithm that computes these polynomials, given that the definition makes sense. Because you can always pick a simple reflection that reduces the length of the larger element. You simply find any reduced expression and look at the last word maybe, and multiply by that on the right, then it will reduce the length, because square is equal to 1, because S is a reflection. So, and when you do that, two things can happen. The length of US can jump up or jump down, and depending on that, you do something different. And amazingly, these R polynomials solve this overdetermined system to define P. That is such a strange definition, but it is one of the most important combinatorial objects that appeared in modern representation theory. So in representation theory, you want to understand modules over, say, Lie algebras. And there are simple modules, and there are certain standard modules that you would like to understand. And by general theory, you know that standard modules admit the composition theories, and each factor should be a simple module, and you want to understand the multiplicities. And these Kazhdan-Lusztig polynomials control these multiplicities for the Lie algebra GLN, or Lie group GLN, if you plug in W equals Sn. And the same story goes for the algebras of other types, and in fact it goes beyond that. So when Kazhdan and Lusztig first defined these polynomials in the 70s, they proposed a series of conjectures, some of them quite advanced, but at least one of them we can state it right away. And it is their non-negativity conjecture. And it simply states that all coefficients of PUVQ are non-negative. So no matter what your W is, no matter what your U is, no matter what your V is, all coefficients of these PUVQ should be non-negative. Of course, they have a series of companion conjectures, which is coherent with this prediction, which shows that there should be some intricate categorical structure which explains this phenomenon. So it was open for a very long time, and was recently proved by Van Elias and Jordi Williamson. In 2014. Okay, so that was the very brief story for Coxeter groups. So let's keep some questions at this point hold them on our minds, and let's move on to the case of matroids. So let's say L is a matroid, and you can think of matroids in many different ways. Right now, I want to think them as a special kind of posets. So I would think of them as finite and graded lattice generated by rank 1 elements. Satisfying the property that the rank of x plus rank of y is at least as large as rank of the join and the rank of the beat. So I have a graded lattice, means that I have a meet and join in my poset. It's a graded, so every element has a height, which plays a similar role of the length in the case of Coxeter groups, which I'll write denoted by the rank. And they always satisfy this inequality. And there's an extra condition that the lattice is generated by rank 1 element. So in other words, every element can be obtained as a join, iterated join of rank 1 elements. So that was the abstract definition, but the important examples are very concrete. And the problems that I'm going to discuss are already unsolved and very challenging in these basic cases of matroids. So there's
by the way, is it the equivalent definition of matroid?
yes. So if you start from some other definition of matroid, this graded lattice L you would call the lattice of flats of a matroid. So here's an example. So you start with a vector space. Over some field K. And maybe you have some finite subset E. And maybe your set L is a set of subspaces spanned by subsets of E. So if you have 4 general vectors in R3, maybe labeled by 0, 1, 2, 3, your L would be the zero subspace spanned by the empty subset of E. And there are 4 one-dimensional spaces, and there are 6 two-dimensional subspaces, and there's a 1 three-dimensional space. And this kind of poset satisfies all the requirements. And you can get many other interesting posets by choosing different E's. These are called representable matroids. Another favorite example would be to start from a graph where E is a set of edges of G. And here your L would be the closed subsets of E, where a closure operator is defined by saying that you can add an edge to the closure of a given subset of edges, and you can form a cycle together with the chosen edge with some subset of edges of the given set. And again, the problem that I'm going to discuss later on is unsolved and very challenging even for this class of matroids or that class of matroids. So if you prefer to concentrate on concrete examples, you may pick either this or that or whatever other setting that may interest you. So in particular, soon going to define Kazhdan-Lusztig polynomials of graphs, any graphs. And so here's a blunt definition, another one. The Kazhdan-Lusztig polynomial PLQ where L is a matrix. So if you remember the setup in the case of Coxeter groups, you see that there is one Kazhdan-Lusztig polynomial for every pair or every interval in a Coxeter group. Here I'm going to define a polynomial in variable q for every matroid. But the setup is really not very different, because one key characteristic of matroid is that every interval in a matroid is a matroid, unlike in the case of Coxeter groups. So if you really want to make them look exactly parallel, you can replace here every interval in L, but that would not give you any extra generality. But still, I'm going to need a notation for intervals, because these intervals will appear in the recursive definition for Kazhdan-Lusztig polynomials. So for f in L, element in the poset or a flat of a matroid, I'm going to denote the interval from the smallest element to f, so everything below f or equal to f in L by L upper f, and L lower f is everything above L. And the key pointer is that these two objects, the two posets, are matroids. Again, the Kazhdan-Lusztig polynomials are defined by a series of properties that it satisfies, and they look somewhat similar. So I want PL over Q to be equal to 1 if the rank of my poset is 0. And 2, I want the degree of my polynomial to be less than the half of rank of L if rank is positive. And 3, and this is the important property, Q to the power of rank L times PL evaluated at 1 over Q is equal to the sum over all flats in my matroid L, and the sum in here is chi of LF Q, L upper FQ, and P L lower FQ. And it is a non-trivial fact that the definition makes sense. So now the question is, what is chi? And this time it is a well-known classical invariant. So in the case of graphs, chi of a q is the essentially the chromatic polynomial of your graph. And in general, it's called the characteristic polynomial of a matroid. So just for the record, to show you the parallel, I'm not sure if you can call it parallel at this layer, but let me try to finish the definition by writing it out. So where chi L of q, so these are determined by for chi L of a q is equal to 1 if rank of L is 0. 5 chi L of a q is equal to q minus 1 if rank of L is 1. 6 if L is a product, L1 cross L2, and chi of L of a q is chi of L1 q, chi of L2 q, and 7 if not, chi L of a q is determined by this deletion contraction formula. So again, in the case of graphs, the deletion and contraction are what you think they are. But in general, L contraction E, where E is a rank 1 element, in L, it's a set of all elements of L that is above E, and L deletion E is the subposet of L that is generated by all the rank 1 elements except E. And I suppose many of you already know different ways of defining this chi, or at least in the case of graph or graphic matrix, it is enough to remember that this chi stands for the chromatic polynomial, maybe divided by divided by q. And it is a small miracle that, again, the definition makes sense. So now we can talk about, for example, Kazhdan-Lusztig polynomials of graphs. And one basic conjecture proposed by people who introduced this polynomial, Ben Elias, Nick Proudfoot, and Max Wakefield, is that all coefficients are non-negative. So I have a work in progress with many of my friends and collaborators. That constructs a theory that is very much analogous to the theory of Ben Elias and Geordie Williamson in the case of Coxeter groups. So it constructs certain algebra, or more plainly, certain sequence of vector spaces whose dimensions encode the coefficients of PLQ, and that would imply the non-negativity of these Kazhdan-Lusztig polynomials. And it also constructs a whole category that more directly shows the analogy that I have shown you for the Coxeter groups and matroids. They both share what is usually called the category O, that is studied by representation theorists, that has many very intricate properties. And from one point of view, this non-negativity is a reflection of the existence of this structure. But one thing that is completely mysterious, but numerically observed in small set of examples, is another conjecture. Proposed by Gedeon, Proudfoot, and Young. And the conjecture states that all roots of PLQ lie on the negative real axis. So this was completely unexpected. So I have a one variable polynomial in the variable Q. It has maybe it has degree n. So in the complex plane, you'll see n zeros. If you run some small examples, and for some mysterious reasons, these zeros all line up. This part is not, it's not an extra information given this statement. So all coefficients are non-negative. So the main point here is that all zeros are real. And I find this conjecture pretty fascinating. So, and I think it's a fair playground for both geometers and combinatorialists. So the one reason why I find this conjecture is fascinating is not just by mere analogy with the Riemann hypothesis type of statement saying that certain zeros align, but also the solution to this conjecture, if this statement is true, would be it should be something non-trivial to either both to combinatorialists and geometers. So the solution cannot be something like this. Oh, if you construct this projective variety and apply this fancy theorem in intersectional cohomology of Herbertius, etc., and then blah, this happens. This cannot happen. Because the same statement for Coxeter groups is not true. And so far as we can see, the algebraic geometry behind these two cases, at least when the matroid is realizable and when the Coxeter group is a Weyl group, is completely parallel. But this statement is only valid in the matroid orbits. So there can not be some black box approach without actually engaging some further intricate geometric property of the variety that behind only matroid case. And also it's extremely unlikely that some highly talented undergraduate student will come up and just look at the definition of the Kazhdan-Lusztig polynomial of graphs or something, and then, okay, you do this induction and just, blah, there's a solution. I don't think this is likely, just because of the nature of the definition. So it's, again, extremely unlikely that someone could approach this kind of statement barehanded without actually encountering the true whatever structure that is producing this phenomenon. So even if someone proposes a combinatorial approach to this, the solution must be very beautiful. That's my guess. And of course, there is another attractive feature, which is that this statement is tested for very, very few matroids. So it may be false. So if you're that kind of person, I think it's worthwhile venturing into computer experience, because the Coxeter group case, this Kazhdan-Lusztig, computing Kazhdan-Lusztig polynomials it's a challenge for a very long time. So, for example, I don't think people can compute Kazhdan-Lusztig polynomials of permutations on 10 elements, just because the naive definition, the algorithm suggested by the naive definition, is not good enough.
For Matroid, it is easier than Coxeter?
I have no idea. I have no idea. Yeah, I mean, computing chi is challenging. So, I don't know. But maybe you don't have to compute chi. I don't know. Okay, but there are some further evidences, small evidences, that there should be a very nice structure producing these phenomena. So I'm going to show you some published and some unpublished statements that are, in a sense, stronger than this level. So something must be going on. One semi-published conjecture is the case of graphs, or maybe in the case of regular matroids. So, informal conjecture is that given that this conjecture is true, so suppose that pretend it's true, and the informal conjecture states that something stronger should be true, and this stronger statement actually suggests one possible approach. The roots of PLQ and PL quotient E, so the contraction of a graph, and both polynomials only have real zeros according to the previous conjecture, and they don't appear in random position. So the expectation is that the roots interlace each other. And the only reason why this is an informal conjecture is that in order to say that the roots interlace each other, meaning that a zero appears and the next zero appears here, next zero appears here, and next zero appears here, and so on, usually presupposes that either the degree of this guy and that guy are the same or different by 1. But it's very hard to predict the degree of the Kazhdan-Lusztig polynomials of graphs. But in all cases, so the precise statement, what it should be is not entirely clear, but at least when L and L of E are non-degenerate in the sense that it has the maximum possible degree subject to this condition. So roughly half of the rank. Then these two polynomials have degree differences at most 1, and in all such cases, tested numerically, this interlacing phenomenon appears. And when something interlaces, maybe there is some inductive way of inductively approaching the easier statement. And let me finish with another conjecture specific to the case of graphs. So if you are interested in testing this type of hypothesis for graphs, the question is, when do these polynomials have the maximum degree, maximal degree? I'm not sure whether that's the expected degree or anything, but it looks like the following conjecture has a chance to be true. So the matroid of any two connected graph is non-degenerate, in the sense that it has a degree roughly half of the rank. So maximal possible degree subject to this condition. So more generally, it looks like connected regular matroids seems to have expected degree, half of the rank. So, and in that case, you can always find E which is satisfied, and you can see if this interlacing phenomenon holds true. So actually, there are some other class of polynomials called the Z polynomials, which have a predictable degree, which have a concrete interlacing conjecture without this annoying non-degeneracy hypothesis. So if you're interested in attacking this combinatorially, I would provide a concrete definition for that. So just to sum up, as a geometer, there is some algebraic variety whose Betti numbers are the coefficients of these PLQ, and that geometric point of view does not help in approaching a statement like this, but at least it gives you one other reason why it is quite intriguing. So usually the Riemann hypothesis type of a statement appearing in number theory algebraic geometry usually concerns single degree in the cohomology of a given object, 1 by 1 by 1. And then there's a action of Frobenius or something else, and then there's somewhat 1 by a polynomial, and you want to prove that these polynomials have zeros all aligned, either in a circle or in a line. But this statement is qualitatively different, so because the coefficients are controlled by Betti numbers living on different degrees, so the usual formulation of Riemann hypothesis is somewhat horizontal, but this one predicts some sort of a relation in the vertical direction. So that some may interpret that as an indication that this statement may not be true, but I think it has been tested on a sufficient number of cases to have the right to acquire further research. I'll stop here. Thanks.
Thank you. Any questions? Yes.
So you gave the definition of this polynomial. So if you apply it on for example, graphing matroid or the trivial case of uniform matroid, can you give like more intuitive like interpretation on these special cases?
So I know for sure that arbitrary graphs are super complicated. So even for complete graphs, it is non-trivial to compute these Kazhdan-Lusztig polynomials. But I believe someone worked out the explicit formula for complete graphs. Maybe not, I don't remember. But whatever special case you're considering it's probably the case that is already non-trivial in that case. Both non-negativity and real zeros property.
Could you give any more intuition about what the coefficients would represent if we could compute them? Or
So yes, that would. So these coefficients have been of central interest in the representation theory community in the Coxeter group case. So in that case, they encode, I think I said this, but they encode composition series multiplicity. So there are obvious representations that you can construct from a given E algebra or whatever. Right? And by general theory, you know that these representations or these modules can be decomposed into simple modules. And you want to understand with what multiplicities each simple module appear. And if you know these coefficients, these coefficients are essentially those multiplicities. So in the case of combinatorics, you can construct an analogous category of what you would call representation theory of matroids. I don't know whether this would warrant interest from the pure combinatorics community yet, but it looks like it's a natural object that is out there, and maybe it has some significance in other cases. For now, we are mostly exploring. But at least I can tell you that, so there are several layers. There's a level of polynomials. This is the version that I presented today. And there's a version you can formulate all these things with vector spaces. And the coefficients will be the dimensions of these graded vector spaces. So PLQ for me at one level is a graded vector space. And there is another layer you can formulate this as in terms of a category. And then these coefficients will be dimensions of certain exit groups category. But at any layer, for whatever special class of matroids, all statements are non-trivial.
Are there some known special cases where no special matroids where these conjectures are already proved?
I'm trying to. I think it has been recently confirmed that it's true for all uniform matroids, but this was a challenge, I think. Even for uniform matroids. I mean, it's trivially true for Boolean matroids and projective geometries. For those things, it's known that the PLQ is exactly equal to 1, constant 1. So actually, the statement that the matroid is modular is equivalent to the statement of the triviality of the Kazhdan-Lusztig polynomial. PLQ is equal to 1 if and only if L is a product of Boolean algebra and projective geometries over finite fields. So for those things, there is no statement about zeros. There is no zero. But it's true, yeah. There is no zero outside the real axis. So you see why I'm saying that the degree of Kazhdan-Lusztig polynomials are non-trivial. So independent of the rank of the Boolean algebra, it's always just equal to 1. But if you truncate the matroid to go to the case of uniform matroids, it's already non-trivial.
Or evidence or observation that says the conjecture of Gedeon, Proudfoot, Young.
So all the evidences are just numerical. Your good friend codes something and push enter. I don't know what's happening inside that computer, and it plots the zeros, and they line up. And then you can go on like, can you compute this for complete graph on 17 vertices and what happens if you delete an edge and so on. And you can play this game. And it looks like that's happening.
You can complete this for a complete graph on 17 vertices?
17, let me not say.
Checking whether
7, I'm sure. 7, I'm sure.
If you give polynomial, it could be practically difficult to say that the roots are on the real line or not, right?
Right. Yeah. But approximately you can, I think, see the picture.
There could be an error.
Yeah, yes.
So the coefficients are integers for sure, or is it?
Yes. They are dimensions of great vector spaces. Yeah, another interesting fact, I have told you about these layers, but let's think about at the level of a vector space. Why do you want to even consider that case? Because many interesting finite groups, let's say finite simple groups, they appear as a group of automorphisms of some very special class of matroids. Maybe you have a very special configuration of points in that projective plane, or maybe just a projective plane that is not over any field or anything. And then there's this sporadic groups and so on. But if you construct all this theory at the layer of vector spaces, then the automorphism group of the matroid always act on those vector spaces. So these hypothetical vector spaces that I'm referring to, giving rise to the coefficients of PLQ, they encode more than the information of their dimension. So they are actually representations of that finite group. So if you have an interesting class of matroids and interesting automorphism groups acting on it, then what you're seeing here is actually a sequence of canonical, if you can say it this way, canonical representations of that finite group. So, yeah, I don't know whether this point of view will be useful for any other purposes, but this is something to keep in mind. So everything is canonical in a certain sense.
Questions? Okay, now let's thank the speaker again.